All right, welcome to this second segment that is part of our conversation about dot products. And this segment is about projections and components, and then a final little subtopic where I'm going to talk to you about work, which is equal to force times distance. So let's take a look at projections and components. I looked at this particular part of the conversation multiple times before I started recording, because I wanted to try to deliver this to you as smoothly as possible, and it might still not come out super smooth. It's a little tricky. I wish I could be like cutting out parts of diagrams and rotating them and flipping them, and I can't. I guess is the end of that statement. But I'm going to do my best to help you understand the idea of projections and components. The first diagram or illustration that we're seeing of a boat being pulled up a ramp or held steady that's on a ramp is a problem that you've seen before. We've seen it with a crate or a barrel on a ramp, and in this particular diagram, the force that's aiming straight down, which is labeled F, is the force due to gravity. F2 is the normal force because it's perpendicular to the ramp. And F1 is the amount of force being exerted on the boat in the direction that goes off to the left down the ramp. And we have been given various pieces of information that fit into this diagram and then asked to find the remaining pieces of information. One of the pieces of information that's very often given to us is this angle measure right in here. And that theta value is the same as this theta value right here. I don't know how you would want to denote that. A little dot maybe there, that's also theta. And what we have done in previous videos is if we're given that this downward force vector is, I don't know, let's say 7, then F2, and we could call this F1, and theta's in there. If we know that F is equal to 7 in the straight down direction, then F2 is equal to F, which is the hypotenuse, times the cosine of theta, because the cosine of theta is equal to adjacent over hypotenuse, which is F2 over F. And so if you solve for F2 by multiplying both sides of the equation by F, you get this equation, F2 equals F cosine theta. Now I'd like you to also try to envision, and I'm going to draw, more terrible illustrations. Imagine there's some sort of a light source over here, and it's just blazing light straight in this direction, in the direction that's sort of pointing up the ramp. And what happens is these beams of light hit this vector capital F, the actual vector, and they cause a shadow, and the shadow is F2. Okay, here's another example of that. If light is streaming down on vector V here, a shadow will be cast under vector V, and that shadow will be this vector here that's being called the projection of V onto W. So again, it's difficult to describe. Okay, I'm going with describing it as a shadow. If you could, I don't think I can do that. What I wish I could do is sort of take this diagram and turn it so that the projection of V onto W was horizontal on the screen. So if you're using printable notes, it might be, if you have printed them, it might be to your advantage to actually take your paper and turn it a little bit so that the projection of V onto W is going sideways horizontally across your paper. That way maybe the idea of the sun sort of aiming straight down on vector V and casting that shadow under it, which here is being called the projection of V onto W, maybe that will make more sense. Now, notice that the projection of V onto W and vector W are pointing in the same direction. They're sort of pointing down and to the right. Okay, so those are pointing in the same direction. Those are pointing in the same direction. This and this, which is really here. It's just bad. It's just bad. That's the projection of V onto W. And vector W, which is in here, are pointing in the same direction, which means they're parallel, which means they're scalar multiples of each other. I could take little vector W and I could multiply it by a number and turn it into the projection of V onto W. Don't forget that. The projection of V onto W. We need a formula. Where's the formula? I guess this is the first version of it. And then do we see the next version? Let's write. I'm going to write out a little something here. I'm going to take both sides of this equation and multiply it by the magnitude of V. The fact that I've written this in green, I guess coincidentally it works out nicely because I have projection of V onto W circled in green over here. Otherwise, the fact that I wrote it in green doesn't mean anything. I wasn't trying to say anything by choosing this color. I just happened to continue writing in green. Okay, so the projection of V onto W, look, we're seeing the magnitude of it here. You can see the length of it over here visually. It's being depicted as having a length, okay. And magnitude of V, right? See the magnitude of V right here? Where's vector V? There's vector V, okay? So the magnitude of V times the cosine of theta, okay? Can you see theta in the diagram? There it is. There's theta. So, okay, yeah, magnitude of V times the cosine of theta is helping me find what we would normally consider to be the length of the adjacent leg of the triangle, which here is being called projection of V onto W. It's a little intense, but really it's just components of a right triangle, okay? V is the hypotenuse, this is one of the legs, this dashed leg here is another one of the legs, it's making a right angle, okay? Don't, just relax, there's nothing really new here, just some notation, just some language. So here's where I would like to tear this thing apart just a little bit further. So we're seeing that, well, let's just read through this box for a second. V and W are two non-zero vectors. That's good. Vector V can be expressed as the sum of two orthogonal vectors V1 and V2 Vector V can be expressed as the sum of two orthogonal vectors. Here's one of them, and here's the other one. And those are orthogonal, right? They're perpendicular. There's the right angle. Okay, so one of those is V1 and one of those is V2. Look in the diagram above that. We've got, there's F, F1, and F2. And F1 and F2 are definitely orthogonal. They meet at a 90-degree angle in that diagram. Okay, so let's come back down here. Expressed as the sum of two orthogonal vectors v1 and v2, where v1 is parallel to w. We're going back. v1 is parallel to w. So it appears that this vector is v1. It appears that v1 is the projection of v onto w. Figure out a way to commit to memory, by the way, how to read that thing. PROJ, subscript w, normal-sized v. I think of it as the v is sort of lording over the w, right? It's higher up than the w is. The w is a bit smaller, so the v is projecting its voice maybe down onto the w. That's how I remember how to read that, as projecting v onto w. I have a lot of these little stories. They're like little characters for each one of these situations, and that helps me remember stuff. Okay, so v1 is parallel to w and v2 is orthogonal to w, so v2 is the one that was going up and to the right. Then v1, okay, so we labeled that correctly. This literally says v1 equals projection of v onto w, which is equal to that mess, v dot w, over w, magnitude of w squared, and then it's times w. What's this w right here? Isn't that supposed to be a vector? I think it is. What about this right here? V dot w. That's a number. What about the magnitude of w? That's also a number. And when you take a number and square it, you get a number. So now you've got a fraction where the numerator is a number and the denominator is a number. You do that division and you get a number. This entire thing is a scalar. It's a number. It's a coefficient on this vector w. So check this out. Keep watching. v1 is a scalar multiple of w. Therefore, those two vectors must be parallel, which means they're either aiming in the same direction or opposite directions. And by the looks of this diagram, v1 and w are aiming in the same direction. They're scalar multiples of each other. v dot w. What is v dot w again? Wasn't there an alternate form for v dot w? Oh, it's the magnitude of v times the magnitude of w times the cosine of our angle measure. Sometimes it's 90, not always though. So this numerator right here, I'm going to take this equal sign up to here, and here's my division, that's my fraction. V dot w is equal to the magnitude of v times the magnitude of w times the cosine of the angle measure between them, and the denominator is made up of the magnitude of w times the magnitude of w. Okay, and then all of that gets multiplied as a coefficient times vector w. Interesting. Well, one thing that I see that happens is that these two magnitudes cancel out. So I've got mag v over mag w, and then there's that cosine theta. v cosine theta, magnitude of v times the cosine of theta. That looks familiar also. Magnitude of v times the cosine of theta. Why, that's the projection of v onto w. Magnitude of v times cosine of theta was the projection of v onto w. But that should be a numerical value. That must have been the magnitude of the projection of v onto w. The projection of v onto w, that's a vector that points in the same direction as w. Okay. And then there's this division by the magnitude of w. And then we're multiplying that as a coefficient into or onto vector w. This looks familiar also. You know, this is really a number, and this is a number, and this is a vector. Okay, so what I'm going to do is I'm going to write this as the magnitude of the projection of v onto w. So there's that magnitude. And we're going to multiply that, still regular multiplication, I'm deciding the order in which I'm going to do this arithmetic. I'm going to take vector w, and I'm going to essentially divide it by, or multiply it by the reciprocal of its own magnitude. Of course, a vector divided by its own magnitude results in a unit vector aiming in the same direction as the original vector. So when we take w and divide it by its own magnitude, we get a vector that points in the same direction as w, but that new vector has a magnitude of 1. So this, you could write all of that down, okay? Unit vector pointing in the same direction as w. That's the short version of what that is. Then we're taking that unit vector that points in the same direction as w, and we're multiplying it by this number, which is the magnitude of the projection of v onto w. So that is the amount, really. That's the magnitude of this resulting vector, ultimately. And the w over mag w gives us the direction. So we know the vectors have magnitude and direction. This is really the magnitude, and this is the direction. And that is equal to v1 on that diagram that's just at the bottom of the previous page. Hi, Sophie. Hi, come in. Yes, I know. We can't be separated for too long, can we? All right, so all of that is equal to, and we can write that down if you want, that that's all equal to v1. So we're bookending it with v1s. Here's a v1, and over here on the left is also a v1. All right, that was so helpful. My hope is that that was actually helpful in helping you make sense out of really what the projection of v onto w is, where it gets its direction, how it gets its magnitude, the fact that you're taking a number and multiplying it by the cosine of theta, and that's helping to sort of find that adjacent leg of the triangle. Okay, so trying to relate it back to things that we already know. And ultimately we end up with this vector v1. Now remember that vector v is equal to v1 plus v2. V is equal to v1 plus v2, and if we subtract v1 from both sides of that equation, then we get this equation, v2 equals v minus v1. So being given vector v and vector w. We could use v and w to do all of this work right here. That would allow us to find v1. Then we would have v and v1, and we could use v and v1 in order to do this arithmetic right here in order to find, oh sorry, not that arithmetic, but this arithmetic in order to find v2. So again, starting with v and w, then we find v1, then we find v2. In that order, v, v1, v2. Thus, v equals v1 plus v2. The vectors v1 and v2 are called the vector components of the original vector. Our original vector was going in some random direction. v1 and v2 are, interestingly, orthogonal to each other. Okay? The process of expressing v as v1 and v2 is called decomposition, or vector decomposition. So example 5, let's see where we are in these notes. I know that we're approaching the 1 hour mark. I know that that was a very long-winded explanation of where that came from, that formula. This problem will be interesting because it's an application of what we were just talking about. And if I split this into 2 videos, then we're not actually pushing the 1 hour mark because this particular topic might well be its own video. So I don't, at the moment of recording, I don't know if this is going to have a couple of segments or not, but I'm starting to think that maybe it should. So, Sophie, what do you think? Meow if 2 segments. Oh, she's busy trying to jump on something. She did a silent meow. We'll probably do 2 segments. Find the projection of v onto w and then decompose v into 2 vectors, v1 and v2, where 1 is parallel to w and v2 is orthogonal to w. Okay, so that's exactly what we've been talking about. Let's use v and w in order to find v1. Put that formula right at the top of the screen. Sophie's trying to climb on the computer. She's climbing on the switcher. She's going to mess something up, no doubt. v1 is equal to v dot w divided by the magnitude of w squared times vector w. Okay, so we need v dot w. v dot w is equal to 3 times 2 plus negative 2 times 1, so that's the product of the I components, or I coefficients, plus the product of the j coefficients, and that is equal to 6 minus 2, which is equal to 4. That's our numerator. We will also need w dotted with itself, so that's w dotted with itself is equal to the magnitude of w squared. Magnitude of w squared is equal to a squared plus b squared, really, which is 2 squared plus 1 squared, which is equal to 5. And that's actually all we need in order to find v1. So v1 is equal to 4/5 times vector w, which was 2i plus j. And if we distribute, we get 8/5 I plus 4/5 j. And there's v1. Not so bad. Now we need to use the other tiny little formula that's up here. v2 equals v minus v1. Maybe switch colors. v2 equals v minus v1, which is equal to, now the original vector v is 3i minus 2j. We're subtracting v1, which we just found to be 8/5. That was the sound of Sophie jumping down from much higher up than she should have been. Thanks, babe. You just almost shut us down. Where are we? Oh, I have no idea what she's done. All right. And we're back. Okay. Sorry about that. 8/5 I plus 4/5 j, so we have to do a little subtraction here, and then we're going to be done with this one. 3 minus 8/5 is 15/5 minus 8/5, which is 7/5 I, and then we have -2 minus 4/5, which is -10/5 minus 4/5, which is -14/5, I do believe, j, and that is vector v2. Remember that v1 is pointing in the same direction as w, they're parallel, and v2 is orthogonal to v1, as well as orthogonal to w, which means if we did v1 dot v2, we should get 0, and if we do w dotted with v2, we should also get 0. You could try both of those and see if you get zeros, and that would also be a way to confirm that you did indeed find vectors that are orthogonal to each other. You could try going through that same process using these vectors. I'm not going to go through that one, but you could certainly come up with v1 and v2 and then check and see if they're orthogonal to each other by doing v1 dot v2 and seeing if you get 0. You could also do, again, v2 dot w and see if you get 0 there. The final little subtopic is this one titled work. Work is equal to force times distance. So F is representing force, and AB with the arrow over it there is referring to distance. Using the alternate dot product formula, which, what was the alternate dot product formula? Was that mag V, mag, yeah, that must have been mag V, mag W, cosine theta. All right, so let's see what we have. We've got a wagon that's pulled along level ground. Let's see what kind of a wagon we can put together here. And of course the iPad's going to bow out right here at the end. And there's a handle that makes a 38-degree angle with horizontal. There it goes. So the handle attached to the wagon, I'm going to attach it down here by the wheel. I'm going to make it a really long handle because I want room to write in that this is a 38-degree angle. And the wagon is pulled along level ground by exerting a force of 25 pounds of force on the handle. So this vector that is the handle has a magnitude of 25 pounds of force. And the question is, how much work is done in pulling the wagon 100 feet? And the wagon, of course, is not going to move in the direction of the handle. It's going to move from left to right. And so I need the force vector that's aiming in the... that's aiming to the right, in that direction. And we can find that using this little formula up here. V dot W is equal to, etc. So I'm going to call this vector V, and I really want to know W? Hi, Sophie. Oh, that was a nice surprise. Appreciate that. Why don't you just stay right there? Impossible. Yeah, you're cute. I don't know if you're that cute, though. Also, I gotta go check this alternate dot formula. Just leave me alone for a second. Don't jump up there. Okay, now that I've peeled Sophie off of my shoulder and ultimately she ended up on my head, I went back looking through the notes, and really this problem is a lot easier than it's made out to be here. And right below me, it says, using the alternate dot product formula. I don't really understand why we would use what we saw in the notes as the alternate dot product formula. This is what I've written here is what we saw. I think, though, that we should be using this idea, that the magnitude of v times the cosine of theta is equal to the magnitude of the projection of v onto w. Because what I really want to know is the amount of force that's being exerted in the direction that's pointing to the right. In other words, what I've just labeled at the bottom of the screen as vector w. That's what I really want to know. And vector w is, in this case, I'm choosing it to be the projection of v onto w. I want that full shadow. So I don't actually know what vector w is. It's a unit vector that's pointing to the right. And so just as we would have done if we were working with a triangle, and I mean weeks ago, if I gave you a right triangle like this, and I told you that this angle measure right here was 38 degrees, and that this hypotenuse was 25, and this was the right angle, wouldn't you find the length of this horizontal leg of the triangle by noticing that the cosine of 38 degrees was equal to x over 25, and then multiply both sides by 25 to get 25 cosine 38 degrees equals x? That's what that looks like to me. So maybe mag v cosine theta equals magnitude of projection onto v onto w. That could be the alternate dot product formula. There's a dot product hiding in there somewhere. Surely, to calculate the projection of v onto w, we could use a dot product. So I'm going with this, and then I'm going into my calculator, and then I'm going home, which was really just something to say. I'm already at home. 25 cosine 38 equals, I got 19.7. 19.7002, please write down all of those decimals, is the magnitude of essentially w. It's the horizontal component vector. We could even label it as the magnitude of w if we want to. Now, in order to figure out the amount of work, let's see, work equals force times. Let's make one little change. Right here where this says W, I'm going to erase that W, and I'm going to have it say F. Which means that over here, I'm going to erase this W and turn it into an F. I'm doing this so that it matches with the printed formula that we have in these printable notes. Right at the top of the screen, W, which stands for work, equals this magnitude of this force vector times the distance from A to B. In this case, AB equals 100, and so work, the amount of work done, is equal to 19.7002 times 100, and when we answer, we're supposed to be rounding to the nearest foot, or sorry, nearest foot-pound, and so this will round to 1970. Oops, just off the bottom of the screen. I have to pull it up and hold it there. Okay, so 1970 is the amount of work done. That took longer than necessary, but I did my best to include the sort of alternate dot product formulas that we'd seen in this video. There are a lot of modified versions of these formulas. You can definitely, I mean, The equation that's at the top of the screen has 5 values in it. So there are numerous ways that you could rewrite even just that one equation. But ultimately, the fact that we could boil this back down to something very familiar, I think, is maybe the most beneficial part about this particular conversation for this problem, because I don't want you to think that we're working on something that's dramatically new. Okay, this is the end of a section. These are applied problems, and we're mixing a little bit of trig and a little bit of vectors, and then we're applying it to a couple of word problems. But at their core, those word problems are not anything super new. All right, so be patient with yourself as you work through these. If you're one of my students, make sure you're prepared to ask questions in class. If you're somebody else's student and you still have questions, pester your own instructor with all of your questions. And I look forward to seeing you again. Thanks so much.